Hi there, thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host, and it's great to have you along again for another episode 381. Coming up, we're going to reveal the name of Australia's moon rover. Yes, we're building one and we're sending it to the moon, or NASA is, in 2026, I believe. It's the plan. But what do you call it? Well, I am going to prove beyond reasonable doubt that Australia has no imagination whatsoever. We'll also be looking at something that affected our ozone layer not so long ago, and this very strange galaxy that's been observed by the James Webb Space Telescope. Well, it was observed, and then it wasn't, and then it was, and then it wasn't. And we'll answer some audience questions about civilization types, tidal locking, and much, much more. All coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to chat about all of that is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. It's drawing to a close. It's 2023, isn't it?
Sure is.
As we speak. So
yeah.
We better fit in as much as we can.
We should do that, and yes, and more. I wanted to show you my new toy. I bought myself an early Christmas present. I don't know if you can see this. Can you see that?
Oh, look at that!
That's
very elegant.
That's the Bolivar lunar watch.
Astron lunar watch. Oh,
yeah. And that's a replica of the one that went to the moon with Apollo 17. I don't know if you can see the inscription on the back, but it names the date and the astronauts and the way it came about, because they actually had commissioned a different watch company to give the astronauts watches, and the fellow who and that was I can't remember the brand off the top of my head now, but
Omega, was it?
Omega, yeah, with Speedmaster.
Yeah,
but one of the astronauts broke his, so he took his own watch, which was a Bolivar.
Yeah,
and they were actually an approved watch for the moon, but they didn't get the first option, and they ended up getting up there by accident, and so voila, they became famous. So got myself one.
Yeah, I knew you were going to show me a watch when you said you got yourself an early Christmas present.
Yeah.
I take it you didn't buy it on a ship, though.
No, not this time. It was on. I bought it through one of my son's girlfriend's mother, who works for a watch company. But they had a I know, they had a Black Friday special, so I got it. I got it nearly half price, so I was very happy.
That's very good. Yeah, that's very good.
But I'm loving it. Loving it.
Well done. So you only had to take out half a mortgage to pay for it rather than the full thing.
Yeah, that's right. Yeah. I really need to get over my watch fascination, but
no, I think you're doing all right.
I've got about 6 of them now. Gosh, I don't know. What should you do? What we should do is get on with it, because we've got to talk about this rover plan.
Yeah.
Australia has been commissioned to to construct a rover which will be sent to the moon in 2026 on a NASA mission, one of the Artemis missions. Now, apparently there were 8,000 submissions sent in to name this rover, and 20,000 people voted on the top 4 selections. Now, the top 4 were Coolamon, Kakira, Mateship, which I kind of like, and Roover, Roover, as in kangaroo, Roover. And the winner is Roover. I mean, come on. 35% of the vote went for Roover. So little imagination. So I am so disappointed, Fred. I really am. I really am.
I can't really comment, because the space agency is very, very close to the astronomy branch where I work. And in fact, the director of the space agency actually asked me if I'd take part in the selection process.
Oh, okay.
Of the name.
I didn't know that.
A couple of months ago. So he asked me, and I said, yeah, I'd be delighted to do that. He said, yeah, Astronomer at Large, that'd be great for you to do that. Yeah, that'd be fantastic. And the next thing I heard, they'd chosen the name. So somehow it just disappeared into the ether and it never happened.
I think you dodged a bullet.
I might have done, yeah, I might have done. I mean, I'm surprised, really, because Kulamon is Kulamon one of the indigenous names for the moon? I think that's the case.
Yes, that's right. And mateship's obvious because that's an Australian thing, but and Kakira is an indigenous word as well.
Yes, that's right. And I was surprised it didn't get one of those.
Yeah, I am too. And there were a few others that I liked. Matilda, I guess they were just sort of hanging on the soccer team's success this year. Bluey. Now, I thought that was a good name. Bluey, the cartoon character, about the blue heeler dog. But Bluey is a dog's name. Rover is like a dog's name. I thought maybe that could work. Then they went with Skippy, like Skippy the bush kangaroo, Wombat, Walkabout. Now, I thought that was good, except the thing doesn't walk.
Yeah,
my favourite, Rover McRover Face.
I was going to say, at least it didn't get Rover McRover Face.
And there was another clever one, but people overseas won't get it. Rover McManus.
Oh, yes.
After the TV host Rove McManus. Although he did work in for America for a while, so some people might know who I'm talking about. And Bert Newton, because his nickname as a TV host in Australia was Moonface.
Moonface, that's
so
right.
And then there's the obvious ones, Steve Irwin, Sam Kerr.
Yeah.
Red Dog, named after a famous movie character that was a dog. Mad Max and Blinky Bill, which is another cartoon character, a koala. But, yeah, it's going to be called Roover. I'm sorry. Honestly, that would have been the last thing I voted for. So I don't know.
All about personal taste, isn't it? It's one of these things.
Come on, Australia.
It's better than C91F42 or something like that, which if it had been an astronomer, that would have been what it was called.
Yeah, I actually like that better than Roover as well. Sorry, I think it's a shocker. But anyway, we're stuck with it. The public has voted, and this is a democracy. Probably shouldn't be after that, but anyway. Maybe there'll be a coup d'etat before we launch this thing, and they can change the name. Let's move along. I think I'm overreacting, Fred.
Well, you are turning out to be a bit prickly about this, I have to say. Andrew. And as I say, I can't really comment because I'm too close to the action. Not that it had anything to do with it, although it was a near thing that I didn't have anything to do with it.
Yeah, like I said, I think you're lucky you avoided it.
Yeah,
but let's talk about this other thing, this supernova explosion, the gamma ray burst that hit Earth a couple of months ago now. But what it did was extraordinary, and what's even more extraordinary is where it came from.
Yeah, so gamma ray bursts, as the name suggests, are bursts of gamma rays. They actually were discovered first in an interesting way, Andrew, because there were spacecraft, because gamma rays don't penetrate down through the atmosphere. They interact with the atmosphere, but they don't penetrate the atmosphere. And so back in I think it was in the 70s, a flotilla of spacecraft were launched to detect gamma rays coming from illegal nuclear atmospheric tests. It was all part of the test ban treaty, the atmospheric test ban treaty. Satellites were put up to monitor the Earth to make sure nobody let off a nuclear weapon clandestinely, because you'd pick it up. Yeah. And what they picked up instead was the celestial version of a nuclear explosion. They picked up gamma rays coming from space, and bursts of gamma rays, which last minutes rather than seconds. Unlike fast radio bursts, which are milliseconds, gamma rays are a little bit longer, but they're typically a few seconds long. This particular one is called GRB 221009A.
That's a great name for a rover.
Yeah, that's right. Yeah, sure you could. Yeah. Ground roving body.
Yes, there you are.
Gamma ray burst. Yeah, there you are. So it's unusual in two ways. First of all, it was very bright in the gamma ray spectrum, and also lasted a long time. I think it lasted 7 minutes. Yeah, 7 minutes long, but was detectable. It's sort of, afterglow, if you can call it that, was still detectable for something like 10 hours. And that contrasts with most gamma ray bursts, because they are detected in gamma rays and then they fade away very rapidly. And so basically a number of spacecraft have been built that can respond to a gamma ray. And this one was discovered actually by two gamma ray space observatories, one called the Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope. Both picked up this thing, and if you can do that, pick up a gamma ray burst before it starts sort of fading away, and that's usually a very short time. What you can then do is alert the ground-based visible light telescopes to go and look at the place where this thing was observed, and that is what is usually the case, but means these telescopes have got to get onto it very, very quickly. Whereas this one lasted for 10 hours, and in fact, there's actually a very nice a time-lapse set of footage that was produced actually by the Fermi Gamma Ray Space Telescope that shows the thing blasting off, and then you could see that it's still there for the 10 hours later. So it was even observable in visible light by amateur astronomers. Work that one out. So this is a really, really bright object. You don't need the world's biggest telescope, ground-based telescopes, to see it.
So if you had a telescope pointed at the right place at the right time, you would have...
Yep. Yeah, you'd have seen it. That's right. Now it's the fact that it could be observed in visible light means you can pick up its distance. You measure its redshift, and it's 2 billion light years away. So this is not on our doorstep.
No.
It's significantly in the depths of the universe. But it actually had made changes to the Earth's atmosphere, which were detectable for quite some time. It's actually the sort of ionization properties of the atmosphere. By that I mean atoms that have been stripped of one or more electrons. These are ionized particles. And it includes the ozone molecules that we know so much about. They're the ones that absorb the ultraviolet radiation from the sun. That's, we've talked a lot about the hole in the ozone layer that came from the use of chlorofluorocarbons in refrigeration, all of that stuff. Well, this gamma ray burst affected the ozone layer. It actually changed the levels.
That freaks me out, Fred.
It does a bit, doesn't it? If you've got something 2 billion light years away that can deplete ozone in the atmosphere, then it just underlines how vulnerable our planet and its surroundings are. Apparently, that effect, the depletion of the ozone, lasted literally only minutes. It was not something that lasted for hours and suddenly irradiated the surface of the Earth with ultraviolet. It was a few minutes, and the ozone layer fixed itself. The atoms, the electrons reunited. So it wasn't a serious event, but it does suggest that if you've got a supernova explosion, and that's kind of basically what gives rise to gamma ray bursts, that's nearby, it's telling you that it can make a significant difference to our planet and its environment.
I would not have expected something that far away to have any impact on us whatsoever.
Yeah, that's right. So would I. It is being touted as a once in 10,000 year event, and is being called a BOAT, BOAT, the brightest of all time.
Is that the same one we were talking about?
I think it might be, yes, because it was last year. It was the 9th of October, 2022. I think we've mentioned it before. Yeah. But what we haven't mentioned before is the fact that it was bright enough to affect the atmosphere of our planet. That's the big news story that concerns this. And it's really quite remarkable.
Do we know its exact origin?
Well, these things, as I said, they're still a bit mysterious. I think they're better understood than when they were first observed back in the 70s. What you've got is effectively probably a supernova. There's still many different interpretations of gamma ray bursts. One is, okay, you've got a supernova that is a star whose mass is bigger than what would allow it just to collapse to a neutron star after the explosion. And if you've got something that's more massive than that, then it'll collapse to a black hole. It's the common formation mechanism for stellar mass black holes. And we know that they release lots of energy, not just electromagnetic energy, but gravitational energy as well, which is one of the reasons why we're getting so excited about the LIGO gravitational wave observatory, because it can detect these events as can other detectors throughout the world. Virgo is the other one, and in Italy, and Kagra in Japan, if I remember rightly. I think I'm remembering the names correctly. I might not be there, but you know what I mean. It's the really high energy end of astrophysics. It's really extraordinary the processes that go on, and there are still some questions about gamma ray bursts. I think it's true to say that we haven't tied them down yet as to what exactly the basic mechanism is. We think that it's partly due to jets of material being emitted from this collapsing star, and that jets have to point in the right direction for you to see them. Jets of material. So there's all that thrown into the mix as well. And to add to the complexity, we've got fast radio bursts, which seem to be something quite different. They are probably flares on magnetars, which are highly magnetized neutron stars. But all these things that, when I started my career, we had no idea about. We didn't even know that there was gamma rays came from space at that time. Amazing stuff. Yeah,
it's quite incredible. I suppose that sort of spawns several questions. What if there's a supernova closer to us? Does that mean we're potentially more exposed? And Betelgeuse once again comes to mind.
Yeah, that's right. Betelgeuse is, 500 light years away, something like that.
Which is a lot closer than 2 billion.
It is, yeah, that's right. So a gamma ray burst from Betelgeuse, yes, would be, especially if it was a boat, a brightest of all time, it would be a bit catastrophic for the atmosphere. Yeah.
Yeah. All right. Well, let's just hope it's looking the other way when it happens.
Exactly. Yeah. If you're talking about material that's being directed out, in relativistic jets, then you do want it to be pointing the other way.
Okay. Well, you can read all about it online. It's everywhere, that story. It's made the New York Times. It's on several websites. It's definitely worth a read. But I imagine, Fred, that someone somewhere will do a bit of a study and write a paper about this at some stage. It seems like it's that sort of topic.
Yeah, there are papers. In fact, I should be able to give you the title of one of them.
Oh, there you are.
Lay my hands on it at the moment. I can't even remember where it's published. I think it's the Astrophysical Journal, and I can't lay my hands on the reference to it. It's a European discovery, just to give you a bit of a closed down. So it's probably in Astronomy and Astrophysics, which is the European journal.
Okay, very good. Yes, and if there's anything more to learn about it going forward, we'll let you know. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's just take a quick break from the show to tell you about our sponsor, NordVPN. Now, a virtual private network is a great way to protect yourself from all sorts of nefarious situations, from hackers to spammers to, just about anybody who wants to get hold of your private information, your bank details, your passwords, your name, sell it to the dark web. Your usernames and passwords are highly valuable commodities. And there's a great way to stop anybody getting hold of them, and that is to use a virtual private network. And there is no better than NordVPN. Now, as a Space Nuts listener, you get a special deal as a NordVPN customer. First of all, there's an exclusive deal available right now for Christmas where you can save quite a few dollars and get extra time on your service. So 4 extra months if you buy NordVPN through our special URL, which I'll give you in a moment. And don't forget, Nord always offers a 30-day money-back guarantee. So the URL is nordvpn.com/spacenuts. When you go to that, you'll see the opening interface. You click on Get NordVPN, and then you can go through all the deals that are available. And there are all sorts of services that you can add on. But it gets cheaper over the longer term of your use. So when I signed on for NordVPN, I went with the 2-year deal, and I got everything, and that worked out to be quite inexpensive. So I'm pretty happy with the service. I'm very happy with the password manager. That is one of the best things ever. I get secure high-speed VPN, malware protection, and tracker and ad blocker. That comes with the basic service. If you go to the next level up, you've got the password manager and the data breach scanner. If you get everything, they'll throw in a 1 terabyte cloud storage and the next generation file encryption. And it is great stuff. I mean, I've been using it for quite some time now. And as I've mentioned before, I've used it in places where I've been able to get online and my wife hasn't, because she's not used the service at that particular time. So it is quite remarkable. And I still don't know how. Sometimes when you're on NordVPN, you get higher speeds than you actually would not being connected to it. So their servers are very, very good. They're all over the world. It is a fantastic thing to do for peace of mind, especially if you're a traveller or if you use public Wi-Fi anywhere you go. Those are where people prowl. Think about it as insurance. A virtual private network is just putting up a wall between you and somebody who wants to use your information or something unsavory that's going to see maybe your bank account emptied. You just don't know these days. There's so many scams around. So check it out, nordvpn.com/spacenuts, and get the deal. I honestly think it's one of the best things I've ever done. nordvpn.com/spacenuts. Now back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, to our next story, and this is sort of a telescopic revelation, initially involving the Hubble, but now with the James Webb Space Telescope up there doing all sorts of amazing things, they've been able to nail this one down a bit better. The popular press is calling this a ghost object because it sort of comes and goes, which is just a popular way of getting people to read your article by putting the word ghost in a headline. But what exactly are we talking about here?
So we're talking about an object. So, it's been called a reappearing, disappearing galaxy, which is what piqued my attention on the news media.
See, they got you too.
They did, because galaxies don't do that. I thought, hello. There's something.
Yeah, what's all this then?
What's all this then? But what it means is we're talking about an object that is visible at some wavelengths and not at others. That's the bottom line.
Okay.
And so this
much less exciting when you say it like that. It's almost as exciting as Roover. I'm going to keep dumping on that.
You are going to, poor old Roover. Yeah, you know, Andrew,
with a name like that, something's going to go horribly wrong.
You've got to, what will go wrong is you'll decide in the end that you like it.
No.
You'll face up to it. You'll think, it's not that bad after all.
No, not going to happen.
Okay. Well, I'll give you another name because this galaxy is not called Roover. It's called AzTEC 71.
Oh, I like that.
It's quite common. Yeah. So it's AzTEC 71. I should have checked what that is an acronym for. It's one of the surveys, one of the many surveys that astronomers are beloved of. They do surveys and then they call the objects a number preceded by the survey name. Anyway, AzTEC 71. So it was first found some years ago by a telescope I used to have a bit to do with, although I never observed with it, the James Clerk Maxwell telescope in Hawaii on the summit of Mauna Kea. That is a microwave telescope which was operated for many years by the Royal Observatory in Edinburgh, which is where I used to work. And so my colleagues were very much microwave engineers. They built the world's first microwave imager, the world's first image sensor for microwaves, which was called SCUBA. And that was a big deal in Edinburgh and used on the JCMT, the James Clerk Maxwell Telescope. Anyway, the object was detected first in those wavelengths which are sort of sit between what we might call the far infrared, the redder than red light that's very redder than red, and the microwave region, millimeter wave region, that microwave region. And so that was when AzTEC 71 was first found. But it was followed up by our old friend ALMA, the ALMA telescope in Chile, which is a kind of super deluxe version of the James Clerk Maxwell telescope with an array of, I think it's 60-odd dishes at a ridiculous height at a place called Chañantor, not far from San Pedro de Atacama, where you're in the northern Atacama Desert. Very, very dry, and that's why ALMA's so good at what it does. So it could be seen in the microwave spectrum that ALMA looks at. Now, the thing is that with an object like this, what you want to do is see it in visible light, and that's enter the Hubble telescope into the story.
Yes.
But it ain't there in the Hubble.
Okay.
And that's why it's an appearing, disappearing galaxy. It's not visible in visible light. And that tells you that you're looking at an object that is a bit peculiar because it shows up in the microwaves and I guess what you might call the far infrared, the sort of stuff that ALMA and JCMT can see, but not in visible light. And the reason why it's coming to the headlines now is that our new toy, the James Webb Space Telescope, which is an infrared telescope, has detected it and indeed given us some very nice images of this object. It's only visible in the reddish, the reddest part of the infrared spectrum that the James Webb Telescope is looking at. So it is there, and it's the fact that we can now see it with an infrared telescope as well as the microwave telescopes, but not in the optical. What it does is that gives you a clue to what's going on here. And it turns out that what you're seeing is a galaxy which is basically enveloped in thick dust, interstellar dust. Now, we know about interstellar dust from our own galaxy. That's what causes the dark streaks in the Milky Way. It's what causes the coal sack, that blob of the black blob devoid of light near the Southern Cross. It's in First Nations tradition. It is the head of the emu in the sky, a typical dusty region of space where there's so much dust that you can't see the stars behind it. And what's happening with AzTEC 71 is that the whole galaxy is in a kind of coal sack. There's dust around it that means that you don't see the stars within it. What you see is the dust itself radiating infrared, because dust actually does that. It gets heated up by the stars and radiates in the infrared. So that's the interpretation of what we're seeing here. A paper published in the Astrophysical Journal with a very, very large number of authors that the paper draws the inference from that that because this object is not visible in optical wavelengths, in visible light, it's not seen in visible light. It suggests that since most of our surveys of galaxies are done with visible light, maybe we're missing a huge number of galaxies that are actually like this dusty galaxy.
Yeah.
They're so dusty that they don't show up in the optical surveys. And so it's kind of potentially opening up a new area of astronomy for scientists who have not really considered this possibility that there's a whole population of dusty galaxies that we're missing, which is a very important piece of work, really. So,
yeah.
University of Texas, Austin, and other institutions, a very large number of authors of this paper, which is entitled "A Near-Infrared Faint, Far-Infrared Luminous Dusty Galaxy at Z of Order of 5 in Cosmos Web." Work that one out.
So if there was no dust in the way, we would see it in visible light?
Yeah, exactly. Yeah. If it wasn't sort of encased in a cocoon of dust, then we'd see it.
Okay. Does that mean we are somewhat hidden from certain angles too? Because there's a lot of dust at the center of our galaxy, isn't there?
Yeah, that's right. And so, yes, if you were looking at our galaxy from the outside, you would always see it because there's not anything like as much dust as AzTEC 71's got. But if you looked at it sort of edge on, so you're looking at the disk of the galaxy from the side, you would definitely see dark markings throughout that disk, very strongly dark markings, which will be the dust in the dust in the disk of the Milky Way, not the dust in the disk of the Milky Way, as I nearly said, but the dust in the disk of the Milky Way.
Right.
So we're a galaxy that's still sort of forming stars. A lot of the material of our galaxy is actually hydrogen, rather than being dust, which is the case in this other one.
So this discovery could open the way for further investigations into other potential galaxies. Now that we've learned this kind of situation exists.
Yeah. So what you do is you get a telescope, well, like the ALMA or the JCMT or the James Webb Telescope, and you do a survey. You do as much of the sky as you can, because these things are visible in those telescopes. The problem is all of those instruments tend to be not what you call survey telescopes, for which you need a wide field of view. So with a survey telescope, you want to observe as much of the sky simultaneously as you can, and then go on to the next bit, rather than having this kind of drinking straw view of a little bit of sky, because then if you try to do a survey with that, you've got a tiny distance between that field of view and the next one, and it takes you decades to cover the sky, if not hundreds of years, depending on how big it is.
Okay, that's fascinating. But if you'd like to read about that, you can find it. You can find it on the AzTEC. If you do a search for AzTEC, you'll find it. AzTEC 71 with double C, AzTEC 71. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Ready for some questions, Fred?
Why not? Why don't we do that for a change?
Okay, we've got one audio question and a couple of text questions that have come in. We'll firstly be heading off to Germany.
Hello there. This is Akshay from Germany, and I'm a huge fan of the Space Nuts podcast. My question is a two-part question. The Kardashev scale is used to define the types of civilizations into type 1, type 2, and so on. Humanity is considered to be 0.7. It's believed that we would be able to achieve this type 1 status in the next 100 years. So my first question is, what do you think about the scale, and is it actually used in astrophysics and cosmology to search for other types of civilizations? And as we know, type 2 civilizations are the ones who can harness the total energy of a star. This is hypothesized by constructing a Dyson sphere around the star. So my next question is that, is it actually possible to construct a megastructure that can cover the sun? Would like to know your thoughts. Love the podcast. Keep up the good work. Thank you.
Thank you, Ashkar. I hope I got your name right. But this is fascinating. We have talked about Dyson spheres before, and we've talked about different types of civilizations and where we sit in that spectrum. What did he say? We're at 0.7. We're just a bit short of being a type 1 civilization. Do you want to expand on that, Fred, before we try and answer the question?
Yeah, and I'm going to cheat because I did write a little bit about this kind of thing in my kids' books. But
I saw you reaching for that.
I had to grab it because I'd completely forgotten about it. And that partly answers the question. Astrophysicists don't really think about this sort of thing. A few astrobiologists do, but the consensus of astrophysics generally and astrobiology is that we could be unique, certainly in our galaxy. So there's not really much point in talking about these civilizations. But let me just read a little paragraph because my Space Warp had lots of little breakout boxes, which we call Tech Talk.
I'll just throw in something before you start.
Do, please.
Just in time for Christmas.
Right.
Space Warp.
Yeah, thank you for Space Warp. Yeah. Yes, it is. Yeah. It's just in time for Christmas. It's a great book, full of cartoons, full of pictures of... Yeah, anyway, never mind. This is not an advert. What I said was, because this is to remind me, because I can't remember all this stuff, it says, one measure of what an advanced civilization can do is the amount of energy it can use. The idea was proposed by astronomer Nikolai Kardashev in 1964, who devised a scale of civilization based on energy resources. For example, imagine a civilization that gathers all the energy from its parent star by building a sphere of solar panels around it. This so-called megastructure is known as a Dyson sphere, named after the physicist Freeman Dyson, who popularized the idea in 1960. If Dyson spheres exist, they should be detectable by their infrared radiation. So far, no one has found anything like this. Now, I'm not going to go into the different types because I can't remember all that stuff, type 1s and type 2s and things of that sort. But the question about, are we as a civilization anywhere near the idea of building megastructures? I think the answer is no.
Well, I'd agree because we can't even name rovers.
I knew that was going to come. There's got to be a clever name for a megastructure that's got kangaroos in it.
Oh, please, no.
Yeah. Anyway, so Dyson spheres.
Yeah, I've got one. Mob mentality.
Oh, I love it. Yeah, I love that. Yes, love that.
For those who don't know, a group of kangaroos is called a mob.
Indeed.
That's the collective noun.
Yeah. So, I mean, all these are really interesting concepts. The Kardashev civilization scheme. Check it out, to our listeners. Check it out. It's very easy to find that stuff online. But there's nothing in astrophysics that leads us to believe that any of this is actually real. And a lot of it comes from this idea, which I think is pretty prevalent among the people who really know about living organisms and evolution and all the rest of it, that the step from a single-celled organism, which might be relatively common through the universe, from that to even an amoeba, a multi-celled organism, is huge. And one of the pieces of evidence for this, if I can kind of get on a bit of a hobby horse here, is that the first single-celled organisms appeared on Earth within the first billion years of the Earth's existence. So it's a very long time ago. And we see them, they're relic stromatolites over there in Western Australia. These are mats of microbes. And they came into existence probably about 3.8, 4 billion years ago. But the first multi-celled organisms were only about 700 million years ago. So there was this long, long period, 3 billion years, where there was nothing but slime on Earth.
Yeah, but you know why it took so long? Because Australians had to vote on what direction to go.
Australian microbes couldn't
couldn't decide.
Yeah, that's right. Well, you could be right there, because a lot of these microbes that the evidence for them, we actually see in Australia, WA, where there are some very
ancient
my case. You rest your case, exactly. But yeah, so going back to it, yes, it's really interesting to hypothesize on what advanced civilizations might do, and perhaps if we manage to survive, what we might do as a species down the track. But I think we are millennia away from anything remotely describable as a megastructure. We've got a very, very long way to go. And you never know. Once we start pulling helium-3 back from the moon, if that happens, we might not need any of these weird and wonderful things, because you can build something the size of a toaster and use nuclear fusion of helium-3 quite harmlessly to produce electricity. That's a slight exaggeration, but that's the bottom line. It's a possibility for nuclear power, very clean nuclear power, that might come down the track.
Fascinating. And Akshar said we're at 0.7 on that civilization rating scale.
I can't remember what that means, actually.
Yeah,
I'd have to look up that.
Well, it's a moot point at the moment, because after the Rover vote, we're back to 0.5.
Yes, okay.
Thanks, Akshar. Lovely to hear from you. Let's go to a question from Tim. Hi, Fred and Andrew. The podcast is Brill. Notwithstanding the names of rovers, he says here. Tim from Burgess Hills, Sussex, UK. My question is, why do planets and moons become tidally locked? Is it because one side of the planet or moon has more mass, e.g. mountains? Will the Earth's ocean tides gradually slow down the Earth's rotation by friction, and then it will become tidally locked to the moon or the sun? I'm lining up some black hole questions for next time. Many thanks, and of course, keep up the awesome work, Tim. I like this question.
Yeah, it's a great question.
As we talk about tidal locking all the time, the moon's tidally locked to Earth. It is drifting away bit by bit. So he's sort of asked a what-if question, but it's real life. It's not a speculator.
No, it's not. It's actually happening as we speak. It's happening. So the probably the way to think to deal with this is to actually answer the second part of his question first. Is the Earth gradually slowing down in its rotation, so it'll eventually be tidally locked to the moon? And the answer is yes. And it's one reason why we have to keep inserting leap seconds into the length of the day, which we've done since the 1970s. I think, if I remember rightly, about 25 times, either on the 31st of December or the 30th of June. There's actually, at the moment, the Earth's rotation is speeding up slightly because there's other forces at play. There's a lot of sloshiness going on in the Earth's core and mantle. But the mechanism for that slowdown, so just think of it in terms of the Earth to start with. What you've got is our planet that's spinning once every 24 hours. It's got the moon relatively close by, which is going around it once every 27 and a half days. And the revolution of the moon in its orbit is in the same direction as the spin of the Earth. In fact, most things in the solar system are. They're anti-clockwise as seen from the north, above the North Pole. So think about this. Here's the moon in space. Here's the Earth. I'm drawing a diagram on my desk.
I can see that.
Yeah, with my fingers. The Earth. Here's the moon. The Earth is spinning, and the moon its gravity is pulling up a tidal bulge on the Earth.
Yep.
Now that, but the Earth is kind of spinning underneath that, if you can imagine it. The tidal bulge is always kind of directed towards the moon. The Earth's still turning. And what it does is, because of friction between the oceans and the Earth itself, and you actually don't need oceans for this to happen. It can happen in solid rock as well. But what's happening is the bulge of the tides pulled by the moon actually drifts slightly in the same direction that the Earth is rotating. And what that does is that adds a bit of gravitational acceleration to the moon, which speeds up the moon in its orbit. To respond, the moon moves further away. So that's why the moon is drifting away. And it's that friction between the tidal bulge of the Earth and the Earth itself spinning underneath. That is the friction that causes tidal locking, because it's gradually over time slowing down the Earth's rotation.
Okay.
And so the same thing would have happened the other way around with the moon. Very early in the moon's history, as the moon was spinning, the Earth would have raised a bulge. Actually, not in the moon. It's not in the oceans of the moon, because it didn't have them, but in the rock itself, which acted as a brake on the rotation of the moon, and so it became tidally locked probably quite quickly in certainly the first billion years, maybe even the first few 100 million years of the solar system. So that's how that process takes place. And yes, eventually, in probably more than 10 billion years, by which time the Earth might not exist anyway, because the sun will have turned into a red giant star. But over time, if nothing else happened, the Earth would be tidally locked to the moon. If I remember rightly, the moon and the Earth would revolve around one another, always facing the same to each other. I think it's 42 days, 45 days, it's about that, rather than the 27 and a half days at the moment, that is the month. So the month and the day become the same length of time, because the Earth's rotation has slowed down.
Yeah.
It's matched the moon rotating around it. By which time, by the way, the moon will be 500,000 kilometres away as well. So it'll be further away. But it will be a stable situation. So we'd never lose the moon altogether. It would wind up in this state. But as I was just saying, the supernova effect will probably overtake it.
Yeah. So is it...
Sorry, the red giant.
Yeah, I knew what you meant.
Not the supernova. Sorry.
We don't want a supernova.
We don't want a supernova, no. And we won't get one with the sun. It's not massive enough. So.
The only good thing about a supernova like that would be it would get rid of the Roover.
Dear.
But I wanted to ask you, is it a coincidence, or is it a part of the effect of tidal locking that our rotation and the rotation of the moon creates that situation where we're always seeing the same part of the moon? Is that part of the same effect?
It is. Just the fact that the moon always faces the same way towards us.
It's not a coincidence. It's actually a part of the effect.
Yes, it's exactly the effect. That's right. And so eventually, as I said, the Earth will be the same. The Earth will always present the same face to the moon, just like the moon presents the same face to Earth. So on one side of the Earth, you won't be able to see the moon at all. You'll never see it. Yeah.
Okay. So nothing to do with mountains, Tim. It's all to do with that other stuff he was talking about. See how much I listen.
You're fretting about that Roover still.
I can't get it out of my head, Fred. I can't. Really bothering me. Thank you, Tim. Let's move on to our final question for this week from Daniel. Hey, guys, I am mediating a question from my father per a discussion we had regarding time and space. We all talk about that at dinner. He's from Nottingham, England, so try not to be biased. His question relates to relativity. How is it possible to measure the speed of anything if an object is relative to many points of reference, e.g. two trains moving at different speeds, to someone standing in the train, a person on the ground, the speed is different? Or more expansively, said trains are travelling at a speed across Earth. Earth is orbiting the sun at 100,000 kilometres an hour. The solar system orbits the galaxy substantially faster and the galaxy vastly faster than that, and so on. So how does one measure the speed of the train relative to anything? I guess the point is, to calculate speed of objects, does one always need a fixed point of reference? But what is that reference point when calculating velocity and distance of objects on an Earth or intergalactic scale? Is the reference point always Earth? If so, why? Thank you kindly, Daniel and Peter. I hope Dr. Watson gets to proofread this before the show. No, he didn't. I just gave it to him then.
That's all right. But yes, it's a great question because, we're taught in relativity, everything's relative to something else. So is there an absolute, the question is there an absolute frame of reference? Is there something that you could say, this is the stationary reference frame of the universe itself? And in a sense, there is and there isn't, if I put it that way. So exactly as Daniel says, we tend to measure everything with respect to everything else. And it goes back to, when I was professionally measuring star velocities by the 100, which we did with the UK Schmidt telescope here up at Siding Spring Observatory, not far from you, Andrew. We always corrected for the Earth's motion around the sun. So what we were doing was measuring those star velocities with respect to the solar system itself. And that's fine. But we know from other considerations what the velocity of the sun is going around the galactic center, exactly as Daniel said. So if we're talking about looking at other galaxies, we correct for our motion around the galactic center. And you could, in theory, correct for the motion of our galaxy with respect to the Andromeda galaxy to get another frame of reference. So there isn't really an absolute frame of reference in the universe. There is one thing that did make people wonder if there was, and that is that when you look at the cosmic microwave background radiation, which is, as you know, the flash of the Big Bang, when you look at that, you find that we've got a velocity with respect to it. I can't remember what it is, actually. It's some hundreds of kilometers per second. And that makes you wonder if what we're really seeing there is the motion of our whole galactic network with respect to the universe itself. And that might be a slightly, just a slightly speculative interpretation, but it has been put forward as being an absolute frame of rest for the universe, the frame of rest of the flash of the Big Bang, because it's as fundamental as we can get. But the bottom line is that, the speed of light, 300,000 kilometers per second, that's been measured many, many times. And in fact, it was kind of predicted as the speed of light before relativity came into being by James Clerk Maxwell. His name's cropping up twice in this episode. He was James Clerk Maxwell, a physicist, a Scottish physicist. He had a theory of electromagnetism which popped out this number C. That's why it's called C, because it comes from Clerk Maxwell's theory. And it turns out that was the speed of light. And it turns out that the prediction is 300,000 kilometers per second. And that matched actually all our measurements of the speed of light, which, by the way, go back to the 1680s with a Danish astronomer by the name of Roover, who measured the speed of light by looking at the way Jupiter's moons behave. And he figured out that some of the things that were a bit peculiar about Jupiter's moons came about because if the moons were on the far side of Jupiter, the light was traveling for a longer distance than if they were on the near side of Jupiter, and he could work out what that distant difference was. So he got a good estimate of the speed of light.
Well.
Well, yes. That's enough about that. But yeah, interesting, relative. It's a good question and well framed.
Indeed. I love that they're having those kinds of conversations. So,
yeah.
And I'm glad they came to us to see if we could, or you could come up with.
I am too.
Yeah.
And look, I don't know, Daniel, whether your dad wins the argument or your yourself wins the argument. But give my regards to Nottingham. It is where my niece lives.
Oh, lovely. Thank you, Daniel. Thank you, Peter. Lovely to get your question. And don't forget, if you have questions for us, you can send them to us via our website, spacenutspodcast.com or spacenuts.io. And while you're there, don't forget to check out the Space Nuts shop, because you might be able to pick up a Christmas edition of Space Warp by someone who shall remain nameless. But if you want a real book, there's other ones in there too. No, it's good. It's good stuff.
It's a good point.
It's aimed at children. That's the one that you wrote for kids, isn't it? So that they can
12 and upwards. People have said it's the best kids book for adults on astronomy. I think that's the problem.
Yes. Well, I'm gathering everyone who wrote it has also voted for Roover or read it. Sorry. But anyway. But yes, do log on to our website to send us questions, visit the shop, or become a patron if you would like to do that and help us keep the lights on. Yes, mine's still on. Just got my electricity bill, so I wasn't sure. That just about wraps it up. Thank you very much, Fred.
Great pleasure, Andrew. Good to have a nice, juicy episode to get our teeth into. We've covered some great ground today.
We sure did. All right. Thanks, Fred. We'll catch you next time.
Sounds good.
See you, Fred. Thank you very much. And to Hugh in the studio who didn't appear today, well, shame on you. The reason he didn't show up is because he voted for Roover. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.